All right, welcome my friends, episode 40. Welcome to Cause. This is going to be a short, I hope it's going to be short. I always end up spouting my mouth much more than I think I'm going to. But we're going to spend the next few lessons discussing cause. This turns out to be everything. This turned out to be absolutely everything. We are after knowledge of cause, especially in science, but in anything. We want to know the explanation for things. We're going to discuss the word explanation and what determines things. We'll discuss the word determine. These are overloaded words in computer speak, meaning they take different meanings and not necessarily related to cause all the time. All right, so this is extremely important. Everything we're going to be doing from now on is we're going to discuss cause, and we're going to go back to Jaynes, and we're going to start modeling. And models are always going to aim for cause. Once we have cause in hand, once we understand cause in all its aspect, which I'm going to discuss, then we have a perfect model because we understand the cause, and we understand the conditions that go into a cause of a substance operating using its powers. And if we know what's going on and we understand the cause, our models will be perfectly predictive. We can have perfectly predictive models even outside of cause, as we'll learn, but we'll understand everything there is to know. Science's goal, of course, is to understand the way the world works. The way the world works is, of course, ontological. We want to know the nature of things, its essence, what's happening. What does it mean? All that kind of thing. That's what we really want. And of course, as we discussed last week, I just recorded the last week's thing. I'm just running these recordings back to back. We want to discuss the epistemology of things. How do we know about this? Because absent knowledge of cause, or a complete knowledge of cause, we can have partial knowledge. Our models have to be probabilistic, correlational. We can only pronounce the way things are probably working. And that's the great, vast majority of models, all right? And the mistake is, of course, every scientist has heard, and you've heard it from me, and you've heard it yourself from other people, correlation is not causation. And every scientist knows this, and you know it. But the temptation, when it's your correlation, to pronounce it as causation is almost never resisted. And people end up, especially when using classical statistical methods like hypothesis testing, so forth, which people fallaciously and absolutely wrongly conclude are confirming cause. So we want to understand all this. Now, philosophically speaking, I'm not going to go into it in any great detail about whether or not we can know cause. There'll be philosophers who endeavor to write books. They labor strenuously to write books to cause you to change your mind to believe that cause exists. Skeptical philosophy and so forth. It makes no sense. It's always self-contradictory. I'm not interested in these kinds of things. There's people who waste a lot of time arguing with these type of philosophies. I'm not going to do this. But it has a consequence. Physicists, for instance, will hear these kinds of philosophies and they'll think, what are these guys talking about? My job, physicists rightly say, is to try to discover the cause of what's going on in these particular patterns I'm seeing and so forth. Or I want to design an experiment to prove my hypothesis about how this causal mechanism might work and so forth. Physicists are absolutely right on the money to do this kind of a thing. And they rightly dismiss the philosophers who say, you can't do that, you can't have knowledge of cause and so forth, that's nuts. The problem is because physicists very rightly reject those screwy modern philosophies of skepticism, they end up rejecting all philosophy and think they don't have a philosophy, which of course is an impossibility. You have a philosophy. No matter what you're doing, you have a philosophy. If you're a physicist and you're creating a machine, an instrument to measure the consequences of some theory, well, you have a philosophy that says my machine will allow me to measure the consequences of my theory. That's a philosophy. That's a form of some kind of verification We're going to get into all that kind of stuff, but you still have a philosophy. And the danger is you'll reject parts of philosophy that are extremely useful. And this is what has happened. This is what has happened. It happened ever since Francis Bacon wanted us to get rid of the morass of scholasticism and their emphasis on cause, the full features of cause. And he was interested in prediction and how we could make things. It doesn't matter if we get the underlying cause right or not. We understand the full aspects of cause or not. Can we make machines? Can we improve human existence and so forth by making good predictions and making good? And there's nothing wrong with that per se, but it leaves out some things, and we end up we exhaust our avenues. If we only think about these smaller aspects of cause. And what's happening right now with quantum mechanics? You know, it's been a century. It's been a century, 100 years of people trying to figure out what's going on with quantum mechanics. Everybody says nobody understands quantum mechanics and so forth, because they picked up this kind of instrumentalist philosophy of eschewing old forms of causality, and are stuck. And we end up with preposterosities. That's my favorite word, preposterosities, like the multiverse and so forth. I've criticized that often enough. Maybe I'll put a link down in the description so you can go into there, in order to overcome the failed philosophies that they're working with. And so that's physics. And then importantly, in statistics and so forth, anybody uses the classical statistics methods, whether it's classical, what they call subjective Bayes, or especially frequentist method, with any kind of hypothesis testing or parameter estimation and so forth. They're widely over-ascribing causality to situations that are no more than correlation and so forth. So we need to understand all that. That's the introduction to the importance of these kinds of things. So I'm not going to talk a lot about it today, but cause, ooh, look at this new pen. Cause has, isn't that pretty? Very, very, it's almost like Japanese writing, I guess. Okay, so cause has 4 aspects. There's a formal cause for a thing. There is the efficient. This is what we're used to dealing with in science, the efficient cause, the mechanics, the material, what is the thing made of, and finally, its purpose. Its purpose, its final cause, the cause of causes, the cause of causes, the cause of causes, the reason all these other causes exist. We're going to discuss all of this kind of a thing. Basically, modern science has kept these two and has thrown out these, and that has led to a lot of difficulties, as we're going to discuss. And we're going to discuss exactly what I mean by all these kind of things. Cause is therefore the word itself. The word itself is analogical. We can't just use the word cause unless we're very careful what we mean in a situation or people take our meaning. Most of the time in science, they mean efficient cause. But cause can mean the formal cause too. And unless we know all aspects of a cause of a thing, we don't know the full cause. All right? And most of the time when we're building models, especially probability models and so forth, we're really only talking about the efficient cause, with the material being sort of implicit to all this. And I know that I haven't explained any of this, but I'm just giving it the background why all this is important. And we've left out these things. And therefore, we don't understand everything perfectly. And that leads to, well, we've heard of the reproducibility crisis and so forth. So leaving out these philosophical aspects of understanding cause is causing great harm in science. Causing, aha. See, every time I use it, that's something. So let me give you an example here of how causality is difficult. So we have this Martian Land Rover. I guess the thing is tooling around up there. Martian rover. And it came across what looks like a device. It's made of rock. And after gathering evidence on this rock, whatever this strange looking thing, it turns out to have something like a display and 2 inputs, or what are, or maybe sensors or inputs. And this may be the display, which I'll just call D. And after monkeying with this, now there's not a lot of time on this. Its bandwidth is low to transmit signals back from this, in the sense that it costs money, not money, but electricity, and so we can't get a lot of information back. But so far, and I'll just translate this to English, math. Basically, there's several theories of the operation of this thing. Nobody can look inside. All we can do is look at how it works. All we can do is see the surface of it. So one theory is that these things are somehow sensing something. They don't know what, but they notice that this thing kind of blips, and this thing kind of blips, and if you add these blips together, well, you get A and B equals the display. But conditional on conditional on this key premise here, that so far they have never seen either A or B 57 or above. 57 blips at any given time. They just never seen this kind of a thing, which necessarily implies that D therefore is less than 113. That's one theory. It's just an adding machine for whatever these things is, whatever these blips are. That's one theory. That's what the NASA scientists say one theory is. Another theory is that, no, these are cosmic rays. They're certain of it because of other theoretical considerations. And it is true that A plus B equals D until if the number of cosmic rays is greater than or equal to 57. Oh, no, I'm sorry. When they're less than 57, the cosmic rays at either A or B is less than 57. And that A plus B then reverts to something like 5 for obscure string theory reasons, or something like this, when X is greater or equal to 57. That's a theory that some people have. That's perfectly fine. Others say, yeah, it's certainly A plus B equals D, because we've seen that. It doesn't matter what the level of D is. But they can see how it seems to have certain reflections in the thing that seems to indicate that this is only true until some date, they think. Whatever the reflections of the sun, and maybe counting certain types of rays and so forth. So they think because of the way the sun's going to change, maybe this is only going to be true. And then after this, it's going to equal a null after the date. And this thing's going to shut itself off. Now, which of these theories is correct? Given the evidence that we have, everybody has the same evidence. Which of these theories is correct? There's no answer. There's absolutely no answer. We could attach probabilities to these things, and we're going to learn how we might do that kind of a thing as we progress along in here. But this is called underdetermination. We've met this before in a way, I think when we did the paradoxes. This is underdetermination. Any of these theories is just as equally supported by the data that we've observed. Each, therefore, there's no just given this and just given the data. There's absolutely nothing to give to distinguish them, except if we knew the cause. Suppose we could get the rover to go over. The rover comes over and it finds a way to look inside, and we discover the purpose of this machine, of this artifact. We discover the purpose of this machine. We discover what it is designed for. And it doesn't necessarily, I don't mean to imply there's always design in science and so forth, but this particular example does. If we can peek inside and see what the thing is for, then we can coalesce to one of these theories. If we know the full cause, if we know the purpose of a thing. And so what does that mean? To say we know the final cause of something, that something is for. So we need to really understand what this means. In order to understand that, we first have to understand what does it mean to even be a thing like an artifact or a natural substance or something like this. So we absolutely need to do all of that. That's basically all I want to do. I can't start on more than this. This is a very short lecture, and people will be grateful for this. But where we're heading towards is this whole reproducibility crisis and the difference between probability models and causal models and all this kind of stuff. Basically, scientists have the idea that, I wrote about this in my limitations of AI. I have a paper, well, blog post I should say, of the limitations of AI. Basically, there's data that goes into an algorithm of some kind, and they think they can discover cause from this, as long as we use AI, which is just a model. It's a model like anything else. That's the hope. And the hope is not wrong. The hope is not the wrong, it's not wrong-headed. It's not the wrong idea to hope for something like this. But look, let me just give you a very common example to show you why we need more than that. We need more than that. So this is a very common example in medicine. So you have a new drug, you give to some patients, and some are cured, whatever the malady might happen to be, it doesn't make any difference, and some not. Did the drug cause the cure? If our evidence is only this, we could put this into an algorithm, we could claim cause. But if you remember the series on epidemiology, if you listen to those lectures, we know that that can't be the case, because it could have been something else that's involved in there. So why don't we just we're always interested in taking greater and greater data. Why don't we record, besides just whether or not somebody was cured, because they all took the drug, the sock color, I like this example, the sock color of the nurse or the physician administering the drug. Why, we could stick this into here and AI will chew on this and give us an answer. But why don't we stick something like this in here? And the reason is, not because we've done experiments or done hypothesis tests and calculated p-values and so forth, because it's obvious to us, using other knowledge, that this has nothing to do with the causal path of the cancer cure, even though we've done no formal tests. So we can reject evidence that's not causal based on other information that we have, that in no formal way. We don't need formal ways to do this kind of stuff. So this is all leading up to hypothesis testing, and we're going to see the absurdities of hypothesis testing. This is one practice that absolutely just has to die in science, die quickly. It's killing science, this hypothesis testing nonsense. It's making people come to all kind of wrong conclusions and vastly over certain conclusions and so forth. And I'm not proving this to you today, I'm just saying it. I'm saying this is the direction we're going. So the hope of AI is wrong, unless the data is such that it's absolutely related to the cause of whatever it is that we're trying to predict. If we have the cause in all its four facets, why then any model, whether we call it AI or whatever, is going to be perfect for us. If we have less than the data that leads to the four facets, then we can't have a model that's perfectly predictive. And we know in some cases in science that we cannot have the data that will allow us to make perfect predictions. For instance, in quantum mechanics, we know because of entanglement and things like this, that we could have some experiment where two particles are entangled, one spin up heading this direction, one spin down that direction in material space. In material space, off they go, and this is measured or interacts with a substance, and it becomes spin down, for instance, and then this automatically becomes spin up. Because of entanglement. These particles are one substance. This is the philosophy part of physics that's missing. These things are one substance, and the interaction means they become part of another substance, or a second substance not related to these first ones, or something like this. But we don't know what it is. We can't know what it is that caused this one to become spin up over here. So we know that we can't always have knowledge of not everything is measurable, is my point. Not everything is measurable. Why do our intellects work the way they do? How do we have free will and so forth? Not everything is measurable. So we are never going to come to a full causal knowledge of some things. So this is going to be where we bump up into all kind of limitations in science, which we'll see when we discuss the philosophy of this stuff. So that's what we're going to do next time. We're going to start talking about a philosophy of nature and sort of trying to play it loose and free like happens a lot of time in physics and so forth. We're going to be very careful about this philosophy of nature. I'm just going to give the outlines to it and point you to where you can go to learn much more about it. I'll defend some of the arguments, but not all of them in absolutely rigorous fashion. To do that would require a separate course entirely. And maybe we could do something like that if there's interest, but not as part of this course, because it would just take us too far astray. Because a lot of people still want to get to the mechanics of, they think they're going to come up with some wonderful new way to make, that's not going to be the case. We're not going to come to some wonderful new way of creating models that allow us to make better predictions and so forth. Up to an extent we will, but like I say, we're going to bump up to, we're going to bump up to the limitations of nature. All right, so that's it. Basically, I'm going to give you some reading to do on this one. This one's going to require some thought on you, so I'm going to spend less time on the lecture today, and you have to spend more time reading. This is stuff that requires quite a lot of thought, because it's all going to be relatively new, or absolutely new to a lot of you, because this is not the way science is normally taught. And so that's going to require quite a lot of new thinking and quite a lot of pondering on your part. All right, that's it for now. Go down below, wmbriggs.com, wmbriggs.substack.com. You'll absolutely need the written lecture and the links to other articles and so forth this time. Next time, we start in earnest on that philosophy of nature. And it's going to get thick for a few lectures, and I apologize for that. There's no getting around it if we want to get this stuff right. Thanks very much for listening. Appreciate it.